Okay, thanks. Good morning. I'm going to talk about a new procedure within Nonlin Look for very high precision absolute earthquake relocation. And I'll talk about this in the context of the relocations of the 2020 M6.5 Monte Cristo earthquake near the Nevada-California border. And I'll discuss how I interpret this as the rupture of a complete shear crack system in the earth. So I'm going to have three main parts to the talk. I'll discuss the new procedure for high precision absolute location, which is called Nonlin-SSST-coherence. I'll show the application to the Monte Cristo sequence and do a general interpretation of the locations. And then I'll discuss how these relocations show rupture of a complete shear crack system. In general, when we locate earthquakes, we start with absolute earthquake location, which forms a foundation and framework for many aspects of seismology, including earthquake response and basic seismological studies. And also for high precision relative locations, you need a set of absolute locations to start with. So I'll be discussing a method for high precision absolute relocation based on the probabilistic global search location in Nonlin Loc. And this procedure already is highly robust to model and travel time errors, so tends to give high quality locations. Additionally, I'll talk about source specific station travel time corrections, a new feature in Nonlin Loc. And this allows the production of 3D maps of perturbed times to use for location. The 3D maps taking into account some of the unmodeled lateral heterogeneity in the velocity model and travel times. And then I'll discuss the high precision relocation, the newest feature, which is based on waveform similarity between events. It's called NLL-coherence, and somewhat related to waveform correlation and similarity procedures used for relative location. So the source-specific station travel time corrections is fairly well established. These are corrections that vary smoothly within a 3D model, and give us a source-dependent correction for each station that you're using and each phase type. In the Nonlin Loc, these corrected travel time fields are developed iteratively and using a Gaussian spatial smoothing of decreasing size throughout the region of interest. So here on the left, it shows for a single station, the SSSTP corrections that are obtained during this iterative procedure at one stage. And at each stage of the iteration, the corrections are added to the previous full travel time field for the station, creating a new travel time field, which can be used for further iteration or at the end for relocation. And it's a little hard to see, but the corrected travel time field on the right shows small perturbations from spherical or circular travel times. So it is indeed a full 3D travel time corrections and travel time fields. As a side note, I think this set of travel time fields one obtains, the 3D set, is in many ways related to a tomographic inversion. But instead of storing the information of the inversion on a single velocity model for each phase type, the results of this sort of inversion are stored as travel times corrections, perturbed travel times for each station. So there's perhaps an interesting relationship there. The second new feature in Nonlin Loc is the Nonlin Loc coherence location. And it's based on the well-known, or the observation for a number of years, that if the waveforms at a given station for two or more events are very similar, and that might generally very similar is having high coherency in in a cross-correlation measure. If two waveforms at a station for two or more events are similar up to a given frequency, then the distance separating these so-called multiplet events is small relative to the seismic wavelength at that frequency. Or in fact, the distance separating the events is small relative to the highest frequencies that are in the waveforms. So here is an early paper doing waveform similarity-based relocation. This is relative location, high precision relative location. The plot on the left shows a set of similar seismograms in a multiplet. The middle panel shows the routine catalog locations based on first arrivals. And the panel on the right shows high precision relative locations based on clustering the events into families and obtaining high precision PNS relative travel times, all using cross-correlation waveform similarity measures. And you can see a great increase in the apparent and presumably real precision of the earthquake locations, increased clustering and organization of the hypocenters. For the Nonlin loc coherence, we also use the coherency defined as the maximum cross-correlation between two waveforms. And the basic procedure is that we have a target event. We're interested in improving the location. We find all the events that have high coherence, high similarity waveforms with the target event. And here, high similarity will be defined as a coherence above some minimum cutoff value. And then the interesting procedure in Nonlin loc, I think, is that when we have the set of the target event and a set of similar events, we combine the Nonlin loc location probability density functions for each event. We combine them all, weighting the combination based on the coherency. So the left panel here shows a set of raw seismograms with the top event is the target event we're interested in relocating, and then a set of similar events with decreasing coherency going downwards. To the right is the seismograms that are actually used for the coherency analysis. It's 2 to 10 hertz bandpass filtering, and also the regions around the P wave and the region around the S wave are separately normalized so that the P wave is not lost, which you can see on the left. Sometimes the P wave will have smaller amplitude and a smaller duration, so it would not count very much in the cross correlation. So it's the seismograms in the right panel that are used for the cross correlation, and also the whole seismograms are used. It's not separately P and S as in relative location. So the P wave and the P wave coda will be important, and also the S minus P time will in general be considered in the correlation. The right shows schematically that the target event, of course, has cross-correlation coherence of 1 with itself. And as we go down into less and less similar events, we get lower coherence. For the Nonlin loc coherence location, we map these coherences to a weight from 1 to 0, where 0 is some user-defined cutoff coherence. So I'm going to show an example from the 2020 Magna, Utah earthquake sequence. The Nonlin loc coherence location for a target event is shown in the left panel with its PDF. The coherence location will form a stack over 3D space of the target event SST location PDF, which is shown in the left panel. And we'll stack that with the PDFs from all other similar events, weighting each of the PDFs from the other events by the coherency weight we've defined. So on the left, we see the target event has a probability density function, which shows the error in the uncertainty in the location of the target event. This is the location using SSST, Nonlin loc SSST. So it's sort of a typical high quality absolute location. You see the uncertainty is the order of 1 to 2 kilometers. On the right, we show the same thing. There's a target event PDF is buried in there. And then I show all events that have similarity above our cutoff with the target event, show those events, epicenters and probability density functions. So we'll take these and combine them, all of them, to improve the probability density function and therefore the location of the target event. So the left panel here is the same as the right panel before. It's all the PDFs from the target event and similar events that we're going to combine. We now make the weighted stack of all these PDFs, weighting by our coherency weighting function. And on the right is what we obtain for the coherency location for the target event. So we can see that we've reduced greatly the error in the location. And now I'll show, again, on the left, it's the original SSST absolute location PDFs for all the events. On the right, I show the resulting epicenters and PDFs for all of the events after coherence location, all of the events of this small family that have high coherence with our target event. So you can see greatly increased clustering and reduced uncertainty relative to the initial absolute locations, and also perhaps some lineations and features in the seismicity. So here I'm showing an example with more complete sequence. This is the 2020 M5.8 Lone Pine, California sequence. And on the left is the USGS routine catalog, epicenters, map view epicenters above and a cross section below from the south. In the middle is a recent paper that studies this sequence and it's showing here their high quality absolute locations using various procedures. And on the right is the Nonlin loc SSST-coherence locations for this almost exactly the same events that are in the other two panels. So this is Nonlin loc SSST-coherence locations following the procedure I just outlined for the full set of events. And what we see is that both the Haukeson analysis and the Nonlin loc coherence results show much more clustering and organization of the seismicity than the routine catalog. This is to be expected because the routine catalog is made to be a simple procedure and able to be produced rather quickly. But also the Nonlin loc coherence locations resemble very much the high quality Haukeson et al. Absolute locations, and perhaps show even more clustering and organization, particularly in the cross section below. You might see this. But Haukeson et al. For this sequence, they also did very high resolution, very high precision template matching relatively location of much larger number of events, 24,000 events. And here I compare the same Nonlin loc coherence locations I just showed with these very high precision relative locations. It's a bit difficult to compare because of the difference in numbers of events, but there are clearly many similar features on various scales, including clustering and lineations. So it seems that the Nonlin loc coherence relocations, the absolute coherence relocations in this case, are approaching the quality and information that's in very high precision relative locations. So the main earthquake sequence I want to talk about is the 15th of May, 2020, MW 6.5 Monte Cristo sequence along the California-Nevada border. This is an interesting sequence because it occurs on left lateral faults, a small region of left lateral faults. I guess there's no scale here. Oh, here it is, yeah. 30 kilometers. So between these blue arrows is something like 100 kilometers. The Monte Cristo sequence occurred in what's called the Mina deflection, which is a major structural right step within a larger dextral right lateral strike slip system in Eastern California, called the Eastern California shear zone, and then the Walker Lane belt system to the north. So it's a little zone of kind of bookshelf faulting, which is left lateral in a larger right lateral system. These are the USGS routine catalog locations. Routine catalogs usually show diffuse seismicity because of the use of simplified, rapid linearized location procedures, often simplified models, general models for a region, and I typically no station corrections. So we see certainly a nice seismicity map, but some diffuse features perhaps showing up. When I take exactly the same events and the same arrival time picks from the USGS catalog, and I do a standard Nonlin location with the EDT misfit function, which is what makes Nonlin loc quite robust to errors for standard location. There is more distinct clustering and features in the seismicity than the catalog. If we now show, I now show Nonlin locations with the SSST travel time corrections, there's increased clustering and definition of features in the seismicity. And finally, applying the full Nonlin-SSST-coherence procedure, we obtain this seismicity, which shows much further sharpening of features in the seismicity and clustering of hypocenters. And this shows the comparison between the original USGS catalog locations and the final Nonlin-SSST-coherence locations. If you looked at the reference, the preprint for this talk, you may have noticed that I noted that the paper was rejected. It was rejected in what I consider to be bizarre circumstances, but the reviewer, I think, who most strongly led to the rejection, it was a one-paragraph review, and in part of that, they stated that effectively the image on the left, going from the image on the left to the image on the right, shows only very modest progress. So be interested if anybody agrees with that or not. So now I'm going to examine what the Nonlin coherence relocations show. I'll show plots like this. On the left is the map view of epicenters, and below a section view from the south. And in the middle, there'll be a map view with epicenters at a narrow depth range. In this case, the shallow depth above 9 kilometers. And on the right, there's a cross-section view from the east, as shown on the middle depth view. So I start with the deepest seismicity, so below 9 kilometers. And basically this seismicity shows two principal on echelon left lateral surfaces, quite linear, which are interpreted as being the locus of the main shock rupture. And they also agree with the overall trend of the seismicity and focal mechanisms such as CMT moment tensors, where the more east-west plane with left lateral strike slip motion is considered the main shock rupture. And this deep seismicity and these two principal main shock rupture surfaces show up in the section view on the right as two near vertical planes. The section here only intersects the western of these two surfaces. Now we're looking at the shallowest seismicity, less than 4 kilometers depth. And in this case, most of the seismicity is to the west, and with scattered seismicity elsewhere, but it's mostly to the west, and also the top of this seismicity and the northwestern part of this seismicity corresponds to the features on the surface map features of dense surface ruptures and fractures, and also after slip identified from INSAR. So it seems that the shallowest seismicity possibly shows that rupture moved to the west and up on the western principal segment, and also that this shallow seismicity is related to, and in some sense a cause of, some of the strongest features that are observed in the surface of fractures and ruptures and afterslip. And what's most interesting in the context of this talk, in the context of shear cracks, is the intermediate depth seismicity. Because on the intermediate depth seismicity, and indeed to the left on the map of all of the seismicity, we start to see lineations towards the limits, at the limits of the principal slip surfaces. And in general, these lineations strike about 40 degrees counterclockwise to the strike of the principal slip surfaces. And they are also subparallel to the regional maximum compressive stress, SH max, which is shown by these arrows here. So what are these features showing us? Well, if we look in a little more detail, the plot on the left shows an oblique perspective view downwards from east-northeast, which aligns your eye a little bit better with these linear features in the seismicity. And the plot on the right is a map view, but the little red lines show the nodal axis of normal faulting events from first motion mechanisms for this seismicity. So the events in the lineations generally show normal faulting mechanisms indicating northwest-southeast extension, subparallel to the regional minimum compressive stress. And strike slip mechanisms, there are also strike slip mechanisms in these lineations. They have pressure and tension axes aligned with SH max and SH min, respectively. And all of these characteristics are those expected for what are called lateral tip damage structures of shear cracks. So what is a shear crack? Or a shear crack system, actually. So a model for earthquake rupture in the earth is rupture on shear cracks. And what I'm showing here is what I call a complete shear crack system. So we have the principal faulting cores shown in red, which are the main shear cracks. But in nature, because of considerations of energy and volume, any shear crack is always surrounded by secondary cracks and features, particularly what are called tip and linking damage zones. So these are shown as yellow and green. And also there are damage zones around the core shown schematically here in blue. So a complete shear crack system would be most of the features in this diagram would form the complete shear crack system. All of these features are identified at many scales in theoretical studies, in numerical studies, in the laboratory with rock fracture experiments, and at the surface through a geologic field investigation. But to my knowledge, seismicity at seismogenic depth does not clearly exhibit the features of a full shear crack system, though people have identified by various means the high strain core and damage zone around the high strain core, and some features of stepovers in particular, which are part of the shear crack system. So what I'm proposing here is that the Monte Cristo seismicity, very concisely, it does look, of course, a bit complex, but in a relatively concise way, is showing the majority of features of a complete shear crack system. So this is a perspective view from the south, looking downwards, and I interpret the seismicity, which is the dots that you may be able to see in the plot. So for example, the large red patches are the principal slip surfaces I identified at depth. And I note that the western principal slip surface, in fact, has a dipping upper part, which leads into the shallow seismicity that I discussed. There is also the step over between the en echelon left lateral principal slip surfaces shown in green. There's some kind of linking structure, which is part of a shear crack system. And then the oblique diagonal lineations that I showed are shown in yellow here, which are tip damage zones, splays, and coming off the ends of each of the principal slip surfaces. There's also symbolically shown a little blue patches, which represent smaller scale damage zone, and particularly damage zones around the fault core. And in purple here is a seismicity that occurred, I think the larger feature here occurred soon after the main shock. The crossing feature further north here occurred a few days later. But this appears to be secondary faulting or independent faulting structures that were activated by the earthquake sequence, and not necessarily part of the shear crack system represented by the main Monte Cristo ruptures. So I stop there and welcome questions, but also a bit of discussion. Does anybody consider or know of observations at seismogenic depth, particularly seismicity, but maybe some other observations that show clearly shear crack damage zones, and in particular, a complete shear crack system? And then how important is it, and is it possible to include larger scale damage zones and fault complexity in source inversion, numerical modeling, and hazard studies? And in the preprint, I particularly have some discussion on the hazard aspects, because it seems that with the seismicity, the Monte Cristo seismicity that is imaged here, it looks clearly like as the rupture to the west moves upwards, activates a complex and large set of damage zones, splays, and so on. But these are related very tightly to the observations of surface fractures and disturbances, which implies that the shallower, the shallowing rupture and the activation of damaged structures at shallow depth is tied to strong shaking and therefore earthquake hazard. Okay, thank you very much.